Hello and welcome. In this video I'm going to be working through the solutions for the Brief Calculus Chapter 2 test review. So without further ado, let's go ahead and jump right on in. So the first one wants us to utilize the limit process to find the derivative. So off to the side I'm just going to write what that template looks like. It'll be the limit as h approaches 0 of the difference quotient, which if we recall that was the f of x plus h minus the f of x, then all over h. So basically I'm going to have to plug in x plus h first. So if I go ahead and do that process, it's going to be the limit as h approaches 0 of, if I plug in an x plus h in place of the two x's that I have, I'd have 2 parentheses x plus h, closed and then squared, minus 3 times x plus h, and then minus 5. And then after that, I have minus the original function, which is going to be 2x squared minus 3x minus 5, all grouped together after that subtraction, and then all over h. So from here, my goal is to now attack those parentheses, or just go after expanding them out. The first parenthesis, I have to deal with the power part before I can deal with the times 2 part. So I'm going to go ahead and just leave the times 2 in front. X plus h times itself, I should get an x times x for x squared, an xh and another xh for a total of 2 xh's in the middle, and then an h times h for an h squared at the end. The next one, distributing the negative 3x through, or sorry, the negative 3 right here through both of those, I'd get a negative 3x and a negative 3h. Then minus 5, and distribute this negative through all 3 of those terms. I get a negative 2x squared, a positive 3x now, and a positive 5. Again, all over h. I'm going to go ahead and just strike through this first one, just distribute that 2 through, so I'm going to go ahead and rewrite this as 2x squared, 4xh, and then a 2h squared. Just distributing that through. So at this point now I have all the parentheses gone, so I should be able to combine my like terms. Looks like I've got a negative 2x squared that can cancel with the positive 2x squared I just created. Positive 3x and a negative 3x, and then a positive 5 and a negative 5. So altogether I've now got, if I go ahead and clean this up a little bit, the limit as h approaches 0 of, looks like I got 4xh. I've got a plus 2h squared, and a negative 3h. Do a quick glance through. Do I see any other terms that are still there? Nope. So it's all over h. At this point I should be able to reduce all of the h's down, and then the last step will be plug in the h equals 0 portion. So if I distribute, or sorry, not distribute, but if I split this fraction up into 3 separate terms, 4xh over h leaves me 4x, 2h squared over h leaves me 2h, and then negative 3h over h just leaves me a negative 3. So if I now plug in 0 for all of the h's, it looks like this middle term is the only one that would cancel out. So for this one, my y prime back on the answer blank is just going to be the 2 terms I see there, 4x minus 3. So I'll just say y prime equals 4x minus 3 here on the blank and call it good. And you can always go back, since we have technically learned the power rule, we could go back and just double check that we got the right answer. So 2x squared, if I did the power rule with, it does turn into 4x, so that first term checks out. Negative 3x does leave me negative 3, so minus a 3, and then the constant at the end does turn into 0, so 4x minus 3 is all good. Moving on now to number 2. Number 2 is wanting us to identify a tangent line. So if we just go through like our checklist of what do I need to create an equation of a line, I'll need to have a point, which what's nice is they gave me a point to go with, so I already have the thing that I need for that portion. I'll need a slope, which a slope is going to come from this part where I'll just take the derivative of it. So to get the m, that's really just going to equal whatever the derivative is, or y prime. And after I have that, I'll just need to use the point slope form, which I'll go ahead and get that out in the open as well. So those are like my 3 main things that we got. We know what our x1, y1 are because it gave me the point -1, -3. I just now need to figure out what is the derivative and plug that point into it to get the specific slope at that moment. So for this one, all I have to do is a few power rules, and we don't have to do that whole limit process like number one. We can actually take advantage of the power rules. So here it would be 4 times 6 in front to create 24x cubed. Then negative 2x squared, the 2 times 2 in front would make a negative 4x to a power of 1. And then the plus 5 at the end technically turns into a 0 because it's constant. So my goal at this point now would be to go ahead and plug in the point that they gave us. So at negative 1 comma negative 3, the slope will equal, looks like I only have to plug in the x value, so it'd be 24 times negative 1 cubed minus 4 times negative 1. So negative 1, if I cube it, it is going to stay negative 1, so this is really a negative 24 minus 4 times negative 1. That's going to switch to a plus 4. So it looks like my slope must be negative 20. So from here I just take those values and plug them into the spots where they need to go in my formula. So my negative 20 here is going to go where the slope is. And then my ordered pair here, I've got negative 1 is going to go where x1 is. And I've got negative 3 is going to go where y1 is. If I go ahead and simplify each one of those, or actually just plug those in, I'd end up with y minus a negative, so plus 3 is equal to the slope negative 20 times x minus the x value, which again minus a negative would turn into addition on the inside. So technically that's one possible answer. You could stop right there. I'm not a huge fan of leaving it in that form though. I'm going to go ahead and distribute through and then also subtract the 3 over just to get it into a slope-intercept form. So I've got y is equal to now negative 20 times x is negative 20x minus 20 minus 3 more. So final answer for this one would be y equals negative 20x and then minus 23. Number 3. This one wants us to do a couple of different concepts. If you remember, average rate of change, that required me to have 2 points. Whereas part B, it wants the instantaneous rate of change, which is just a single point. So the first one, average rate of change, really is legitimately just find the slope from a point that has an x value of negative 1 to another point that has a x value of positive 1. So what I could do is just figure out what those 2 points are. So the first one's negative 1, comma, and then whatever happens if I plug negative 1 in. Well, if I do negative 1 to the 4th, that would be positive 1 times 2. And then minus a negative 1 would switch to plus 1, so 2 plus 1, that would give me 3. So there's one of my points. And then the other one, if I plug in positive 1, I end up with 2 times 1 minus 1, so that would just turn into 1 comma 1. So now finding the slope, I can do it in whichever order I want. I'll just do y2 minus y1 just to start there. So it's going to be 1 minus 3 over a 1 minus a negative 1. So that will switch to 1 plus 1, so it looks like I've got negative 2 over a positive 2, which equals just negative 1. For the next part, it wants us to figure out what is the instantaneous rate of change. So this is more of a derivative concept. So I'm going to do f prime and actually just plug in the value that it needs. So if I go ahead and just kind of think like that's what I'm going to need to do, let's go ahead and get the f prime out. So I'm actually going to switch that back to an x for this part. Just so we can kind of see where things are coming from. Once again, power rule with this one, 4 times 2 in front turns into 8. Power then drops by 1, so 4 turns into 3. And then minus the derivative of just an x is going to leave a 1 in that spot. And so now let's figure out what's f prime of 1/2 if I were to plug it in. So if I plug in 1/2 and cube it, that turns into 1/8. So I'd end up with 8 times 1/8. Then minus 1, so it looks like I've got 1 minus 1, which equals 0. So this one, the instantaneous rate of change at 1/2, actually gives us a value of 0. So that must be actually a horizontal tangent line for that specific ordered pair. All right, number 4, this one wants us to just do a higher order derivative. So what the indicator is this is wanting f double prime. So remember that just means I need the second derivative. So if I need to get to the second derivative, obviously I'll need to find the first derivative. So that's where I would begin. So this one Looks like I don't have any products or quotients or anything weird, so I'm just going to use a couple of power rules. So f prime of x is going to start with 5 times 2 gives me 10, and then the power drops by 1, so a new power is 4. Then minus 3 times 8, that's going to be 24. x2, the new power is 2, and then plus 3 at the end for the derivative of 3x. Now I can go ahead and jump to what's the second derivative, so looks like I'll end up with just 2 terms left here because the 3 is a constant that will turn into 0. Just like before, it's going to be power times the coefficient, so 4 times 10 gives me 40. New power is 1 less, so power of 3. And then 2 times 24, that's negative 48. And then new power on that, I don't know what the heck that just was, 48, there we go. And then the new power on the x is just going to be a power of 1, and like I mentioned, the constant's just going to turn into 0. So my f double prime here of x, or the second derivative of f, would be that 40x cubed minus 48x. Moving on now to the next page here, we got number 5, just wants us to do a fair amount of derivatives, each one having potentially a little curveball compared to the prior. So it looks like it just kind of glancing through at least letters A and B, I have got a couple of things multiplied out, so I could do this as a product rule, or we could take the time to expand out and turn it into more just a power rule type situation. So I'm going to go ahead and model this just utilizing the product rule, but realize you could technically take the time and just multiply that out, maybe using an area model, combine your like terms, and then just take individual derivatives from there. But like I said, I'm going to go ahead and just model this with the product rule. I'm going to call this first part my A, my second part B. And so if I needed to find the derivative, the format I'm going to have for y prime is going to be A times B prime added with b times a prime. And again, that's just the pattern that product rule follows. So if we go ahead and do that really quick here, my a is going to stay the same, so 4x cubed minus 1 is going to stay grouped up, then times the derivative of b, so x squared would turn into 2x, plus 3x will turn into just a plus 3. Then I've got added with b times a prime, so my b this time is staying put, x squared plus 3x. And then times a prime, well, the derivative of that looks like it's just going to be 4 times 3 is 12, x, and then the new power is a 2, and then the constant turns into 0. So at this point, I need to start multiplying things out, make those parentheses go away. So again, that's kind of why is it worth your time initially to just multiply it out so you can get to this part a little bit faster, or just earlier in the problem. I guess it's not that much faster. But I may have some higher powers to deal with when it comes to expanding a step earlier. So each one has its little merit as far as like when I should do the multiply out. I'm going to go ahead and just, again, continue with this pattern here. I'm going to distribute through the 4x cubed and just write down what I get. So 4x cubed times 2x, 4 times 2 gives me 8. X cubed times an extra x is an x to the 4th. Then 4 times 3 for the next one will give me a 12. And there's no x for it to combine with, so x cubed. Now move on to the negative 1, distribute it through. It looks like I get a negative 2x and a negative 3. Next one, all I have to do is distribute the 12x squared through, so 12 times 1 will stay 12, x squared times x squared is x to the 4th, and then the next one, 12 times 3 will give me a 36, and x squared times x gives me x cubed. So final answer for this one, if I go ahead and combine my like terms, looks like I've got 8x to the 4th plus 12 more for a total of 20 x to the 4th. I've got 12 x cubes and 36 more x cubes, so that's going to take me up to 48 x cubed. And it looks like I just have a negative 2x and a negative 3 that weren't able to really combine with anything. Letter B, on the other hand, I really wouldn't have the option to multiply out, so this is one where I would have to use the product rule, just because the square root and a cube root really don't interact with each other very well. So this is again going to follow that a times b pattern. So on the far left, again, still going to utilize this guy, doing a times b prime plus b times a prime. For this one though, I might recommend just right off the bat getting rid of those radical symbols. So this really is the same as saying x plus 2 to a 1/2 power, And then the other one is an x minus 3 to a 1/3 power. And then from here, it's just going to be a matter of how do I apply the power rules. And this is also kind of a chain rule, but at least the kind of nice part of this is the inside derivatives each time are just going to be a 1. So I'm not going to have to worry about doing a whole lot with the chain rule portion at least. So if we go ahead and get the ball rolling here, we got y prime will equal, I'm going to go ahead and do a times b prime first. So that means the x plus 2 to the 1/2 is going to stay unchanged. But then I multiply by the derivative of the second one, or the b, so that would be 1/3 comes out front. My base of x minus 3 stays the same, and then my new exponent is 1 less than 1/3. So it's really like I'm subtracting 3/3, so it's going to go down to a negative 2/3. Then I would add that with, this time I'm going to take the derivative of the second part, or sorry, I'm going to keep the second part, so x minus 3 to a 1/3 is going to stay put. And I didn't leave myself a lot of space. This will now be times, I'll have the 1/2 comes out front. My base of x plus 2 would stay. And I'm already close to the edge here. This is now going to subtract by 1, so it would be a power of negative 1/2. Sorry if that's hard to see for that part. But anyway, if I go ahead and now look at what we've got, I'm going to go ahead and rewrite some things where I move things from top to bottom because I got a couple of those negative exponents, and just maybe try and clean this up a little bit. Shouldn't take up as much space. So I've got x plus 2 to the 1/2 power that's just staying in the numerator. I've already got a 3 as a coefficient on the bottom from the 1/3, and then that x minus 3 with the negative power will go just right after that, and it has a 2/3 power. The next term, it looks like I've got x minus 3 that would be the only thing left on top to a power of 1/3. Then over, if I go ahead and look at what I've got here, I've got a 2 that's already on the bottom from the 1/2, and then that x plus 2 being raised to a positive 1/2, now that I move it to the bottom, would be what we got now. So our options from here would be to find a common denominator and combine if we would like. We could also just leave it as is. So for this one, I'm going to go ahead and show the extra part, but realize that technically would be an acceptable answer right there. That is at least demonstrating we know how to deal with the negative exponents. We've already got the power rule situation taken care of. We remembered product rule. All the kind of required elements there. It's just a matter of the end answer there doesn't look super nice. And what will be kind of nice with this one, if I multiply the top and bottom by the other denominators, I actually end up completing the square as well as completing the cube for each one of these. So this first one, I would just have to multiply it by the other denominator, so times 2 and x plus 2 to the 1/2. And as long as I'm doing that on top and bottom, that's creating that common denominator of a 6 with an x minus 3 to the 2/3 and an x plus 2 to the 1/2. The second one, I just have to multiply by the 3 and the x minus 3 to the 2/3 times 3x minus 3 to the 2/3. And now listing out everything that would be in the numerator, I can go ahead and just make this one single denominator. 3 times 2 actually gives me the 6. X minus 3 to the 2/3, x plus 2 to the 1/2, and then technically here, when I take the x plus 2 to the 1/2 and multiply by the other x plus 2 to the 1/2, that's now an x plus 2 to the 1 whole, so I could just distribute 2 through, and that will give me a 2x plus 4. And then the next one, if I multiply the x minus 3 to the 1/3 by the x minus 3 to the 2/3, that completes that to make it 3/3. Or I can just distribute the 3 through, and that would turn into a 3 times x and a 3 times a negative 3, which would give me a negative 9. So getting closer to my final cleaned up answer here, I should just be able to combine the like terms in the numerator. 2x and 3x make a 5x. 4 with a negative 9 make a minus 5. So I could technically factor a 5 out of that, but I don't think I'm going to take the time to do that because that wouldn't cancel with anything on the bottom anyway. So x minus 3 to the 2/3 and x plus 2 to the 1/2. Again, you could rearrange the bottom as well if you wanted to have the 1/2 written in front of the x minus 3 to the 2/3, but to me, again, that seems like kind of a waste. It doesn't really make it look that much cleaner. But at least now, instead of it being 2 fractions, it's just a single fraction. So that would be where I would personally go, but like I mentioned before, what we had in blue earlier in the problem could technically be an acceptable answer because you've established what the derivative really was. All right, letters C and D now, if we transition to those, these ones now are going to be a little bit more quotient rule oriented. So maybe off to the side here, I'll go ahead and just say if we have like a y is equal to a divided by b, my formatting for that's going to be low d high, so b times a prime, minus high d low, so a times b prime, over the square of what's below, so over b squared. So I just need to follow that pattern and take the individual derivatives as I encounter the primes, and then make sure that I don't forget to maybe distribute a negative through because of that subtraction in the numerator. So if we go ahead and get the ball rolling with this one, we've got y prime equals b times a prime, so it's going to be 2x plus 1 times the derivative of the top. Well, the derivative of the top is going to be 2 times 5 for a 10, and a new power of 1 after it drops by 1. Then it's going to be minus, now it's going to be high d low, so keep 5x squared, but then times that by the derivative of the bottom, which is just a 2. And then all of that's now over a 2x plus 1 that is now all together getting squared. So just like product rule, now our goal is to just try and clean up the top a little bit if we can. So I'm just going to distribute the 10x through the two terms there, and technically this doesn't really have any distributing on the second one. It's just a negative 5 times 2 for a negative 10x squared. But if we go ahead and just write out all these things, we can combine that afterwards. So 2x and 10x gives me 20x squared, and then 10x times 1 is a positive 10x, and then I've got the minus 2 times 5 is 10x squared, as I just mentioned, still all over 2x plus 1 being squared. So now the last step would be combine any like terms, so it looks like I've got 20x squared and then minus 10x squared for 10x squared plus 10x all over 2x plus 1 being squared, which I kind of noticed there. I could factor, if you wanted to, I could factor a 10 and an x out of the top. That leaves me x plus 1. Unfortunately, it still doesn't really cancel with the bottom, so this is more of a unnecessary step, if you will, but it makes things a little bit smaller. At least the powers on top seem a little bit smaller, so it would be kind of an either or with this one. I'd be okay with this answer, or you can go with this answer. They both would be correct. Letter D is going to follow that same pattern, but again, kind of similar to letter B above. I do have a square root, so I might recommend just right off the bat, just writing that as an x plus 1 to a 1/2 power, just so it's a little easier to see how that power rule part is going to work. So for this one, there we go, we've got our original rewritten, and now it's just going to be follow that same pattern. So if we go ahead and jump in, it'd be the bottom function times the derivative of the top function. So this is 1/2 going out front, the base x plus 1 staying the same, then the power dropping by 1, and then technically it's times the derivative of the inside. I forgot to mention that on the previous one, but timesing by 1 really is not going to change a whole lot, so I'm going to go ahead and drop that. But technically we are multiplying by the derivative of x plus 1 at the end for that chain rule portion. Then it's going to be minus the top function, so x plus 1 to a 1/2, and then times the derivative of the bottom function, well, 4x squared, that's going to give me 8x, and then minus 6, that turns into a 0, so it would just be 8x. Then all of that's now going to be over the 4x squared minus 6 as a quantity being squared. So from here, we now would look to see if there's anything I can do to clean things up. I noticed that we've got a negative exponent, so that technically means it would be in a denominator. So we could just rewrite that as a fraction in the numerator. So it'd be a 4, actually I've got a 1/2. I can go ahead and just take through that 4x squared minus 6 and reduce those to like a 2x squared minus 3, and then I no longer have this 2 that's in the denominator, so that cleans that up a little bit. Over the x plus 1 now to a positive 1/2 by dropping it to the denominator of that term. Then minus, here it looks like I just have an 8x That's multiplying with an x plus 1 to a 1/2 power. Just kind of move that in front as far as just, again, making it look a little bit more natural. And then the bottom is now 4x squared minus 6 still being squared. So to clear this smaller fraction inside of the big fraction, I could just group everything up on top and multiply through an x plus 1 to a 1/2 power. As long as I do it on top and bottom, it's like I'm multiplying by 1, but that should actually allow us to kind of cancel this denominator that's in that smaller fraction when I do the distribute this part through. So if I distribute that through to the two terms, my first part in the numerator is just going to leave the 2x squared minus 3. Then I've got a negative 8x that's now multiplying with, if I do x plus 1 to the 1/2 times another x plus 1 to the 1/2, add those two powers, I just get x plus 1 to the first power. So it looks like I'll be able to just distribute a negative 8x through and clean that up pretty quick. And then the bottom now is going to be 4x squared minus 6 squared, but still times the actual x plus 1 to the 1/2 that I just was distributing through on top. So the last step, if we maybe just foreshadow, if I distribute those through and combine like terms, I'd have a 2x squared from the front minus 8x squared for a total of negative 6x squared. Then I've got a negative 3 and a negative 8x, so I'm going to go ahead and just put the negative 8x next and then the negative 3 at the end. And then all of it's over the 4x squared minus 6 being squared times the x plus 1 to the 1/2, which if you wanted to switch the 1/2 powers back to square roots, or the 1/3 power back to a cube root in the previous problem, or one of the previous problems, by all means you can do that. It's just not something you have to do. In fact, with this one we could go even through and maybe distribute, or not distribute, but factor out a negative from the numerator and just make it one single negative in front of the whole fraction. But again, that's not something you have to do. That's just more of a personal preference, cleanup type idea. I feel like that's actually a good place to stop, so I would go ahead and stop there. Now moving on to the last two on this page. Looks like letter E, we've got a chain rule situation because we've got a function inside of another function. So as far as the format is concerned, I'm just going to have to do the outside part. So if y, let's go ahead and see how we can write this. If y is equal to f of g of x, the derivative of that y prime is going to be f prime of g of x. So notice the inside would stay unchanged, but then times the derivative of the next level. And if I had another level, I'd end up just continuing that same pattern. But for this one, it looks like I just have the two parts. I've got the power of 5 as the outer function, and then the 2x cubed minus 1 is the inner function. So if I just start out here, I've got f prime of x as my notation. The 5 is going to move out front as a coefficient, just doing the power rule portion. My base is going to stay the same, so 2x cubed minus 1. The new power on that, though, is now a power of 4. So that so far I've taken care of this f prime of g of x. So notice the inside part did not change. And now I'm going to do times the derivative of the inside part. So if I just focus my attention on just those two terms there, derivative of 2x cubed will give me 3 times 2 in front for a 6x, and then the power drops by 1 to a 2. And then the derivative of negative 1 would just be 0. So it's just going to be those two terms there. So if I now just combine the stuff that's outside of this kind of bigger grouping with the power of 4 on it, I can say f prime of x is equal to, see, if I do 6 times 5, that would give me 30. X squared I can move out front, and then I have my big grouping there that I can't really, or probably don't want to more than anything else. I don't want to have to expand that power out. I would just leave it in that format. So this is a decent, at least things combined a little bit, but still in factored, not fully expanded format. Now on to the last page. So last page here, kind of scroll down a little too far, so let's go back up just a little bit. But for the first one here on the next page, it just wants us to do what's called implicit differentiation. So just as soon as I saw that, that meant I probably am going to see some x's and y's together, which if we look at our function, we end up having. The trickiest part of this one probably is this x times y. I'm going to have to do like a product rule for that portion. Everything else is going to be pretty straightforward, but if you recall from hopefully the lessons, remember anytime I take a derivative of the letter y or something that's just not the letter x, I'm going to have to do the extra like chain rule portion, which would be multiply by the derivative of y with respect to x, which really is just going to be create a bunch of these, or I guess not a bunch of them, but create a couple of those dy over dx's. So since I see two y's, I'm expecting I'm probably going to have two cases where, or two places where I'll have a dy over dx get involved. But anyway, let's go ahead and just jump right on in. I'm just going to take the derivative of each of these with respect to x, and again, the with respect to x has to do with the dx in the denominator right here. So if I go ahead and look at what each one of these would turn into, x squared is just going to be a 2x times technically dx over dx, which is really just a 1, so I don't have to worry about that. Plus, here I'll have to do the product rule portion, so I'm going to do let's just keep the x first, and then times the derivative of y with respect to x will be dy over dx, then added with, so that right there I just did the a times b prime, so now I'll do b times a prime. So this will be keep y and then multiply by the derivative of x, which is again just a 1, so I can close that off. Move on to the next term, so I've got y squared here that I'm now doing, so 2 would move out front, power on y would drop by 1, so it's now a power of 1. But because of chain rule and that being a different letter, I'd have to do times the derivative of the y part with respect to x, so hence the dy over dx. Then the next term I move on to is the minus 6x. That's going to be pretty quick and easy, I hope. It's just going to be a negative 6. And then the easiest one of all of them, the derivative of 4, since that's a constant, that's just going to turn into 0. So now essentially I just look at what I have. I do have the plus and then parenthesis here. I don't really need those parentheses, so I'm going to get those out of the way since it just had a 1 in front of them. And now I'm going to move everything that doesn't have dy over dx over to the other side. So to me it looks like I've got to move these three, oops, not that one. Ignore that, sorry. That was a plus. And let's see, I've got the negative 6, I've got the positive y here, and the 2x. I can just move all of those over. So I'm going to add 6, I'm going to subtract y, and I'm going to subtract 2x. So that way all three of those have now moved over to the other side of the equal sign. Now notice I've got two terms here that both have dy over dx attached to them, so I'm going to go ahead and just factor that out since the whole point of this is to try and get it to where it's just one of those. And so if I now factor that out, the first term would leave the x, the second term would leave the 2y, and it does have a plus in the middle. Everything on the other side is just going to be a 6 with a negative y and a negative 2x. As long as you have those three, the order doesn't matter. As long as the negative is on the y and the 2x, we're all good. The very last step of this would now be, let's divide by that parenthesis. And if I could do any reducing, oops, that's a x plus 2y, not 2 plus. So x plus 2y in the denominator. If I could do any reducing, I would. But I can't really factor it, doesn't really look like, so that actually is as good as my answer will be. So you could write this as dy over dx, or you could say y prime, whichever your preference is, and then it's just going to be whatever that fraction is we just created. So 6 minus y minus 2x all over x plus 2y. Okay, moving on to number 7. This one's a little bit more of an application of derivatives problem. They're providing us with a position function. They're naming it s, and so it wants us to identify a velocity at a specific moment and then actually just come up with what the acceleration function is. So my answer for part 1, or part A, is going to be more of a numerical answer, whereas my answer for part B, since it actually just wants the function, it's likely going to still have t's all over the place with that one. But if we look at what we got, it's given us this position function that's written as a fraction, so I could do a quotient rule approach, or I could do a rewrite it where I move it to the top and just make it a negative power on it, and then do this more as like a chain rule approach. So kind of personal preference which way you would like to do it. They both should end up at the same place. I'm going to do more, I think, the chain rule approach instead of the quotient rule, but to each their own. So anyway, with this one I'm going to go ahead and kind of identify how do I get to each of these processes. Well, if they gave me a position function, the first derivative of that would be the velocity, and then the second derivative of that would be the acceleration. So kind of think the acceleration will be the derivative of the velocity, so I kind of have to get the velocity equation first. So let's go ahead and start there. For velocity, I'm going to go ahead and just name it v instead of using s prime, but technically s prime would be correct. If I go ahead and start the process here, I'm going to deal with the more chain rule part, so I'm going to use this version, not the original version. So if I do that, the -1 would come out front as a coefficient. The base of t squared plus 4t would stay the same, and then the power now drops by 1. And now on to the second part of chain rule, which is the derivative of the inside. So the derivative of t squared plus 4t is going to give me 2t plus 4. So my options there would be to maybe rewrite it using fraction. Since I do have a -2 as a power, I could write this actually as a -1 times the 2t plus 4, which I could distribute that negative through if you wanted, and then have that over t squared plus 4t being squared now to a positive 2 on the bottom. Regardless, with this one, it just wants us to figure out what is the velocity when the time is 2. So it's pick one of those two and actually just plug in, not t, but plug in 2. I think actually this newest version is the easiest. So I've got negative, let's see, 2 times 2 would be 4 plus 4, so that's going to be 8 over t squared. That's going to be a 4 plus 4 times 2, that's going to give me 8 being squared. So that's really a -8 on top, and then 12 squared on the bottom, that's 144. If I bring a calculator in and reduce that, looks like I can divide 8 out of each of those, so I've got a -1 over 18 as the result from a calculator. And this does have units. Velocity here, if we're talking height, is in feet and time is in seconds. That's going to be feet per second. The fact that this came back negative would just imply that at that moment in time it must be falling, not rising. And in fact, it technically is falling at a rate of 1 foot every 18 seconds, if you want to think of it that way. That's kind of a weird way of thinking of it. So it's kind of slow. Must probably be like near a high point if it was going up to begin. I don't know. We'll find out, I guess, if we wanted to look at a graph of this and how that would be modeled. But again, this just wanted us to identify the velocity at that moment in time. We got our velocity equation, plugged the number in, and simplified, and we got -18, or 1/18 of a foot per second. Anywho, moving on to the next part, part B, it wants us to do the acceleration. So this is going to be kind of a personal preference of, do you want to do a more product and chain rule part here, or do you want to do a quotient and chain rule part here? To me, it's kind of flip a coin type situation. Neither of them is necessarily that much easier than the other. I think most probably, if you had to choose, would choose the product over the quotient rule, but that's mainly just because you have an addition sign and not a subtraction sign, which sometimes that subtraction sign can get a little tricky. So I think I'm going to do the product rule approach just to show it, but we do have the option. We could go with a quotient rule. Regardless, they both have a chain rule part when we do the derivative of the t squared plus 4t being raised to a power portion. But anyway, we're finding the acceleration, so I'm going to go ahead and name it a of t. And if we go ahead and start the process doing the a times b prime, that means I'll keep the first part the same, so -1 times t squared plus 4t to a -2 power times, now the derivative of the second part, well, the derivative of 2t plus 4 is just a 2. Then I'm going to add that with, this time I keep the second part, so the 2t plus 4, that's not changed. But now times the derivative of the first part, this is where that chain rule portion gets involved. -2 times -1 is the coefficients, now a positive 2 in front. The base of t squared plus 4t doesn't change. And the new power is 1 less, so that would be a -3. And then times the derivative of the inside part, this is where that chain, or a second half of chain, works. Derivative of t squared is a 2t, and derivative of 4t is just 4, so 2t plus 4. So now at this point we would just look to see if we can maybe clean some stuff up and maybe combine some like terms for our final answer. I think we're probably still a couple of steps away, but if I look at what we got, we've got a couple that have negative power, so I'm just going to drop them to the bottom. The -1 times 2 will stay on top though, since they don't have the power, so it would be -2 over t squared plus 4t, now to a positive 2 power since I moved it. Then it looks like I've got plus another fraction going on. I've got a 2t plus 4 and another 2t plus 4, so that's actually 2t plus 4 being squared. Then I also have this extra 2 that doesn't have that negative power, so that's going to stay out front of that, and then it's all over t squared plus 4t, but this one's a negative 3, so it's going to be a positive 3 power once I drop it. So to get a common denominator, it actually doesn't seem overly complex. I just have to multiply by 1 more t squared plus 4t. And as long as I do it on top and bottom, it's like I'm multiplying by 1. That should now allow me to write this as a single fraction over the t squared plus 4t actually being cubed, now that I've made them both have a power of 3. And if I distribute some things out, it looks like I've got a negative 2t squared, negative 2 and 4t is negative 8t. And let's see, expanding this power of 2 out, that's going to give me 2t and 2t, so I'm going to go ahead and just keep the 2 in front. 2t is 4t squared. 2t times 4 is a 8t. I'll get another 8t for a total of 16t. And then a 4 times 4 would give me an extra 16. So if we combine some like terms, looks like if I distribute that through, I'd have 8t squared minus 2t squared for a total of 6t squared. I've got negative 8t, but then I would add 32t to that. So 32 take away 8, that's actually positive 24t. And then 2 times 16, that's just going to give me a plus 32 at the end. And then all of that's still over my t squared plus 4t being cubed. And again, we name this a of t, so I'll go ahead and just use that name in front, and voila, we've got to our final answer. It looks like we could maybe factor out something from the top since I have some even numbers, but again, that's not a necessary step. That's just a personal preference step. So I think that's a good stopping point. If you can handle this problem on the review, I guarantee the question you have on the test is going to be way more manageable. This one got a little ridiculous pretty fast, but again, hopefully just describing and seeing like how we can approach it multiple ways at least gives you an idea of, okay, here are the things I need to think about. But I promise the question on the test is not going to be as intense when it comes to finding the accelerator or acceleration part. I'm going to probably simplify it, make it a little less quotient rule or product rule-ish, or at least maybe take away some of the chain rule part. But anyway, hopefully that was able to be followed along. If not, you know where to find me. Hopefully you can come ask me some questions. Maybe we can work through it and try the quotient rule approach if you would like to see it that way. But we could also do that just in class as well. All right, now finally to our last question, number 8. This one's a little bit more of a related rates, so one of the more recent or later lessons in the chapter. This one, it actually, I just noticed, has a typo. That's not supposed to say sphere, that's supposed to say circle. My apologies for that. So the radius of this circle, it says, is increasing at a rate of 2 inches per minute. So if we maybe kind of point out that this is a radius increasing, that would be like a change in r per change in time. So dr over dt, it's saying is a 2. So any dr over dt's I get, I'll get to put a 2 in that spot. Then it wants us to find the rate of change of the area. So this is technically saying that for both of these parts, I want to figure out what is like dA over dt. So that'll be the unknown that I don't know. And then it looks like it gives me 2 different scenarios where I just need to figure out what would happen if I plug in an r of 4, and then what would happen if I plug in an r of 18. So let's go ahead and just maybe get that derivative portion taken care of. It's kind of nice. It's actually provided in case we forgot the area of a circle. Probably did remember that, but a equaling pi r squared, or the area equaling pi r squared for a circle, shouldn't be too big of a stretch, but again, it provided it for us. So now I just do my derivative of that with respect to t. So it's really just going to be like d over dt of that expression, a equals pi r squared. So if I take the derivative of that with respect to t, a is just going to turn into dA over dt, equaling pi is just a coefficient, so I'm just going to let it kind of hang out. R squared, its derivative is going to be by chain rule, 2 comes out front, r is the base, the new power is 1 less, so power of 1, but then times the derivative of the r with respect to t, so that's going to be a dr over dt. So that's where that 2 that I identified at the beginning is going to get to go. So if I go ahead and now plug in the values that they provided, all of the dr over dt's are just going to turn into 2 like we have there. And then the r right here, oops, I meant to change color. The r right there, I don't know what's happening here, it's a little slow. My r right there is going to either be a 4 one time or an 18 the next time. So for part A, this one's just going to be, I got a bunch of white space, may as well take advantage of it. So I've got A equals 2 pi times the radius 4 times the dr over dt 2, which looks like I get 8 times 2 for a total of 16 pi. And in this case it would be area, so square inches per, and then the time unit was minutes. So there's my first answer, 16 pi square inches per minute. For part B, it's pretty much the same thing. I just am plugging in a different number for the radius, so it's going to be 2 pi once again times, I'm at the radius, so that's where 18 would be, and then times the change in r per time, so that's dr over dt 2. So it looks like I've got, what, 18 doubled, that would be 36, doubled again, that would be 64 pi, and then square inches per minute once again. 64 pi square inches per minute. Probably could have just wrote it there instead of at the bottom writing it twice, but regardless, it's on there. Anyway, hopefully this video has been helpful, but if you have any questions, as per usual, just come find me. Let me try and come up with something. Maybe we can work through another example if there's a specific type of problem that you would like. But yeah, anyway, like I said, hopefully this helped. Appreciate you taking the time watching it, and we'll catch you next time.